Good evening. Welcome to tutorial session 8. I hope you can see my screen. Good evening. So, in this tutorial session, we are going to cover problems on root locus and also on state space representation. So this is basically course on classical control, which takes care of transfer function, not the state space equation. So there is only introduction part. So I have few questions only with the introduction, like how we represent the plant in terms of equations. Okay. So let me briefly explain or just cover the what is covered in this week week 8. Okay. Okay, so in the previous week, in week 7, we started with one problem involving gear transmission. So we had two shafts, input shaft and output shaft, coupled with an gear. So we have input gear of N1 teeth, okay, and output gear with N2 teeth. Okay, so what we are trying to do is we are trying to develop the transfer function. This is actually the plant. So we are trying to develop the transfer function between output and the input. So for this particular gear transmission, the output is the load torque and sorry, not the load torque, the output theta 2, and the input is the torque. So the input torque is the input and the output is theta 2. Okay, so we are trying to get the transfer function. So how to get that transfer function? We use this free body diagram for each shaft and got this equations. Okay, so governing equations we have, so 1 and 2. So also we have some relationship between theta 1 and theta 2, so relating number of turns. So if you say this, okay, so based on that we got one transfer function. If you substitute all the values, you get a single equation and between the input and output. So if you take the Laplace transform, you'll get the uh, theta 2 in terms of input torque and the load torque. So this load torque we are taking as disturbance. Okay, so that's why we are not considering this. So we have neglected this load torque TL, and directly we got the transfer function between theta 2 and Tm. So theta 2 is the output and Tm is the input. So this is the plant transfer function. Okay, so this is the transfer function, and we have substituted few values a and b, so that this plant transfer function looks very similar to what we have studied. Okay, so you can see, you can relate to this transfer function, right? Okay, so this was covered in week 7. Okay, so this is how we start. Okay, so we are given with plant and we try to develop the equations, then we get to the transfer functions. And if we have if we have the plant transfer function, we try to develop the control. Okay, so these are the tasks, so that we have to control, or we have to develop the controller so as to satisfy these things. So what we have to satisfy is settling time and the maximum peak overshoot. So this is the condition. Okay, so how we are doing it? We are using the root locus that we have studied in the previous weeks. Okay, so we have, in this case, in this particular case, we have just chosen a simple proportional controller. Okay, so proportional controller only has a gain of kp. Okay, so by using root locus, we are trying to get the range of kp. Okay, so that we get this settling time under 2 seconds and np less than 10%. Okay, so what should be the value of kp? So for that, we try to so we got the what we got this coefficient. So if you see for a second order system, so what is the coefficients? Okay, so for two poles s1, so plus minus j. So if I just write the common terms, okay, so we are relating the uh, settling time with this value. Okay, and also from the peak overshoot we got the zeta value. From that we can get the beta. Okay, so how we are relating to this in the S plane? Okay, so you can see here, so this is the angle. Okay, so this is the angle that we got from the peak overshoot. Okay, and if you see what this minus eta omega n is the real value. Okay, so it's just minus 2 here. So we try to develop the root locus by using all the steps from step 1 to step 6, and by using the root locus we got to the value of kp. Okay, so what should be the value of kp so as to satisfy those given conditions? Okay, so this is basically, this was the task. Okay, so after all performing and drawing the kp, we got the kp value between 8 and 35.76. so this is how the root locus was used to design the controller value. Okay, so again in today's tutorial I'm going to do one question where we will be developing the root locus and we will be choosing the value of kp, because you know kp can be from 0 to infinity if we take the positive value of kp. Okay, but using this parameters and this root locus we are able to constrain our kp value between 8 and 35.76. Okay, so this is we have seen. Okay, so again we have seen the state space representation. So this is again one of the alternative methods to design the controllers. Okay, so we are not studying this, we are just using the transfer function approach. So basically we are given with an equation and we try to write that equation into n first order ODE. Suppose we are given with second order ODE, then we try to convert into two such first order ODEs. Okay, so we have to choose state variables. So what are state variables? These are those variables whose knowledge at each and every point stand of time is sufficient to completely characterize the system. Okay, for in case of mass spring damper system, so here we have taken two state variables as, so x1, this is displacement, we have taken as one state variable. Okay, so this is displacement. Okay, so other is like velocity, so this is dx by dt, so this is again velocity, we have taken other state variable. So using, because this is of order 2, you can see this. So if you see this state, this equation. Okay, so this is of order 2. So we are trying to get two first order ODEs by you choosing two state variables. Okay, okay, so actually we are defining, if we see here you can get the two equations. So these are two equations. Okay, so this is one equation, another equation is given by this. Okay, so we to try to write these two equations, first order equation in terms of matrix. Okay, so this is how we write. So this is the general x dot equal to ax. Yeah, I think someone's mic is on. Okay, Surya Narayana, can you please switch off your microphone? Okay, x dot equal to ax plus pu. Okay, so we try to develop, this is a matrix for CISO. Let's take for CISO. Okay, this is all matrix. So what is A called? A is called state matrix. Okay, X is your state variables and B is your input matrix. Okay, so simply we'll write the all the equations in this form. Okay, so this is state equation, so this is called state equation. Already that's, you can see it's written here. Okay, so this is the state equation, and other equation we get is the output equation. Okay, so in terms of state variable and the output, so this one. Okay, so these two equations completely define our plant. Okay, so y equal to c xt plus d into ut. Okay, so this is state equation and one is output equation. Okay, so this is complete state space representation. Okay, So this is used in modern control theory. So this is advanced control system once you study this. Okay. So since because in this case we are only deriving the transfer function for the causal linear systems, but this state space equation can also be used for the non-linear systems also. Okay, so that is one advantage. Okay, so if we know ABCD, then you can realize the system. So what we have studied here, you can see the LTI causal system. So what is difference between the transfer function approach and the state space representation approach is shown here. Okay, so one main thing you can see is we are analyzing in the T domain, so we are not converting into any domain. Okay, so if you see uh, the transfer function approach, we used to convert from the time domain to the S domain. Okay, and we used to always get a unique transfer function, but in this case you'll not get the unique. This is non-unique in the sense it depends on what state variables you choose. Okay, for if you choose a different state variable, you will get the different number of uh, equations, first order equations. Okay, based on that your plant will differ. Okay, but ultimately what you want to do is to control, right? Okay, so basically this it's shown how you can write the same equation with these multiple input. Okay, so this is how to get the transfer function. Okay, so basically you can see here, this is, I'm just highlighting the main formula that how to get the plant transfer function. Okay, so basically you just use these two equations. Okay, and just take the Laplace transform and write output in terms of input. Okay, that's what it is written here. Okay, if you see this equation, and what is the transfer function? Y of s by u of s. Okay, which is this. Okay, if you substitute these values, you will get the transfer function. I think one question is also there, so I will do one question, so more clarity on that. Okay, so this is one example problem that professor has already solved. Okay, and also one thing to notice here is the poles of transfer function is also the eigenvalues. Okay, so how to calculate the eigenvalues? This is how you will calculate the eigenvalues, and what you will see is eigenvalues and the poles will be same. Okay, so it's already written here. Poles of PS are same as eigenvalue of A. So for any matrix, this is how you calculate the eigenvalues. So I've just highlighted here. Determinant of lambda I minus A equal to 0. Okay, and we know how to get the poles of a transfer function. Okay, okay, so just they have started one frequency response topic. Okay, so in this case, what is frequency response? We are just in this case, input is the sinusoidal. Okay, so deals with response of the system when a sinusoidal input is provided to it. So the plant is same, only just US is not this, instead of step or ramp or impulse, we are giving the sinusoidal input. Okay, so you can see this is the sinusoidal input. So this is, they've taken the Laplace transform. Okay, so this is the derivation, and finally we are concerned with this. Okay, so at steady state, what is happening? So if you see at steady state, your y of t is equivalent to, so you'll get the sinusoidal. Okay, so you if you can remember, if our input in the previous case, if you give the input as step, okay, so the output was also step, right? So it depends on like what type of over dam system, under dam system, okay, critically dam system, depends on that. But in this case, what is happening, you are getting the sinusoid. Okay, at t equal to infinity, y of t is a sinusoid of same frequency. Okay, and what is happening, your magnitude is scaled by the plant transfer function. Okay, so basically if you read this, the steady state output is sinusoidal signal of same frequency, okay, as that of the input, but scaled in magnitude by p of j omega and shifted in phase by phi angle. Okay, so it is property of LTI system. Okay, so how to get the sinusoidal transfer function? You just place j omega instead of s, equal to j omega, you will get the So here example is also shown here. Okay, ps equal to 1 by s plus 1. Just plus put s equal to j omega, you'll get the sinusoidal transfer function, and you can get the magnitude as well as phase. So this is how you can get the phase. So this is very important. Okay, so how to get the phase and the, so this is the magnitude. Okay, so this is how you'll get the magnitude, and this is how you'll get the phase. Okay, so up to now we have covered. Okay, so in the next week we will cover the Bode plot. Okay, so we can, how can we visualize this particular type of system? Okay, when the input is sinusoidal. So first is Bode plot, that we'll study. Okay, so up to now, any doubt? Okay, okay, I'll go to the tutorials questions. Okay, so it's, I'll read the question. The open loop transfer function of a negative feedback closed loop system is this, where k is non-negative real valued parameters. The closed loop system is stable for only. Okay, so in this question you can, it's very simple. You don't need to find the root locus also, but how you can do it, because what's given, Plan transfer function is given. Okay, k by, okay, let me choose the blue one. So this is open loop transfer function. Okay, with negative feedback closed loop system. Okay, k by s square plus 4s, and it's also given, it's a negative feedback, it's given, and k is non-negative. That means k is greater than 0. Okay, so closed loop system. So very straightforward step is you find the closed loop transfer function. Okay, so what is closed loop transfer function? gs1 plus gs into hs. Okay, let's assume it's a unity negative feedback system. I think it's given open loop transfer function of a negative feedback. Okay, it's not given, but we'll take hs to be 1. Okay, let me write the general formula, and hs is equal to 1, unity feedback system. Okay, negative unity feedback system. Okay, so let's find out the closed loop transfer function. Okay, k by square plus 4s plus 1 plus k by square plus 4s. Okay, so this is k by s square plus 4s plus k. So it's very simple. This is closed loop transfer function. And how to get the stability, how to confirm the stability? Okay, so you just take the characteristic equation. So what is characteristic equation? Let me write as ts, which is denominator square plus 4s plus k. Okay, so this is the characteristic equation, and what we used to do is we'll find the roots of this, and the roots of this is, these are also called the poles of the closed loop transfer function, and those roots or the pole should be lying in the left half of S plane. Okay, so that's how you confirm the stability of the closed loop transfer function. Okay, so in this case this is second order, okay, equation. So it's very straightforward. So you can use the Routh's stability criteria also, and also we know all the coefficients should be positive in this case. Okay, straightforward, because if you see all the coefficient for s square, it's 1, coefficient of s is 4, and the k, okay, so the constant term has to be positive. That means it has to be non-negative. So straightforward, it's very simple. We know if k is greater than 0, okay, so if k is greater than 0, we'll ensure that the poles of this equation s square plus 4s plus k will be lying on the left half of S plane. Okay, so if you see, this is S plane. Okay, so if we ensure k to be greater than 0, then we are ensuring that the poles are lying in this plane. Okay, and if poles are lying in this plane, what we say, the system is stable. Okay, it's very straightforward. So but let us prove this, okay, by constructing the root locus. Okay, let's construct the root locus, because we have studied. So any doubt up to now? Okay, so let's construct the root locus. So open loop transfer function is given to us. So again I will write gs is k by s. Let me write s square plus 4. So I'll write s plus 4. Okay, so where k is greater than 0. Okay, and also what is given, it's a negative feedback system. Okay, so if you just refer your notes, you'll be using set 1 steps. Okay, what is set 1 steps, if you remember from the last week? Okay, so it's concerning the odd multiples of 180. Okay, so we'll construct the root locus. Okay, so again, you know, the answer is this is the answer. Okay, we're just doing the additional part. It's very straightforward. So by root locus approach, we'll see. Okay, so we are trying to develop the root locus, and you'll see how if k is greater than 0, all the roots are lying on the left hand side, okay, of this plane. So what was step 1? Okay, so let's find out what are the zeros and poles. Okay, so first zeros. Okay, so if you see how many zeros are there here, so you can see m is equal to 0, right? There are no zeros here. Okay, so if you see the numerator, only k is there, so number of zeros are equal to 0. So m is equal to 0, so let's take the poles. Okay, so n is 2. Okay, so what is the location, if you see? So p1 is at origin, which is 0, and other pole is at -4. Okay, so if you see the denominator part, if you equate the denominator to 0, you'll get the poles. Okay, so these are open loop poles and zeros. Okay, okay, let us plot this. Okay, so only two poles are there. So one is lying at origin, okay, and other is at -4. Okay, so this is the step 1. Okay, very simple. So what is step 2? Okay, so you'll find out on the real axis, okay, where the root locus is lying. Okay, that is the step 2. Okay, so just copy this. Okay, now tell me. Okay, let's take 3 regions, right? So we have classified 3 regions here. Let me just, so 3 regions are this -infinity to -4. Sorry for that. Okay, -infinity to -4, and this is the first region. Okay, so let me write here -infinity to -4. Okay, and the second region is from -4 to 0, and third region will be from 0 to infinity. And we are just checking where the root locus is lying on this real axis. Okay, so what we used to do, simply we used to take the test points, right? So let me take this test point st1. Okay, so I've chosen this st1, and now what is the next step? Okay, just see to the right, and if you have odd number of open loop poles and zeros, we'll say the root locus exists there. Okay, but if here in this case, what you see, even number of open loop poles and zeros. Okay, so the number is 2. So what we can say, the root locus does not exist. Okay, so the root locus does not exist because of even number of poles and zeros lying on the right hand side of the test point. Okay, so let me choose other test point here between -4 and 0, st2. So what we can see, so just see to the right of this point is T2, only one pole exists. Okay, so the number is even, right? One is one is odd, right? So we can say the root locus will exist between -4 and 0. Okay, so if you see the third region 0 to infinity, okay, so what you can say, so no real, not real, yeah, okay, no real 0 or pole exists. Okay, so 0 is even, so you say root locus does not exist. Simple. So what we can say, the root locus exists between -4 and 0. Okay, so this thing is clear. Okay, so this was is test point 3. Okay, so doubt up to now here. Okay, next is finding the asymptotes. Okay, first is how many asymptotes will be there. So number of asymptotes, okay, which is equal to n minus m. Okay, n is the number of poles and m is number of zeros. Okay, so which is 2 minus 0. Okay, you see 2 minus 0, okay, which is equal to 2, and we have two asymptotes. Okay, that means two root locus will be going to infinity. Okay, so again directly by seeing this, you can see here, okay, there are two poles and no zeros, so you can be certain that these two, there will be two root locus and that both the root locus will be going to infinity. Okay, let's find the angle of asymptotes. Okay, so which is, okay, this is n minus m. Okay, so 2k plus 1, then we have, if we place 2. Okay, so there are two root locus. Okay, so you can take plus 90 and minus 90. Okay, or you can say this is 270. Okay, so two asymptotes, so they are making, one is making 90° with the real axis and other is making minus 90° with the real axis. Okay, so again what we have to find out, point of intersection. Okay, so point of intersection of asymptotes. Okay, what is that? Sum of poles. Okay, so this was sum of poles. So when I say poles, it is open loop poles, right? Minus sum of zeros. These are open loop zeros. Okay, minus n minus m. Okay, so what is number of poles are 2. Okay, so they are lying at 0 and -4. Okay, so number of zeros is 0 and minus 2 is 2. Okay, so minus 4 by 2 is minus 2. Okay, so again what, let me draw the root locus. Okay, okay, let me draw the root locus here. Okay, and we just now have found this. Okay, I'm just drawing the asymptotes. Okay, okay, so this is the asymptote. Just okay. Okay, so this point is minus 2. Okay, so this angle is 90° and this angle is, so just writing this angle is minus 90°, or you can say it's a 270°. Okay, so this is up to step 3. We have drawn the root locus. Okay, so this is 0 minus 4. me write this outside. Okay, so this is assumed. Okay, so this is asymptote number 1. Okay, and this is asymptote number 2. Okay, okay, so we have covered up to step 3. So what was the step 4? Okay, we are finding the breakaway and break-in points. Okay, so I want to ask you a question here. Okay, so we have two poles, open loop poles, lying on the real axis, 0 and -4. So what do you think? What will have, break-in or breakaway point?
Breakaway.
Okay, so this is like root locus will start from here, from one pole, -4, and from 0. Okay, so at open loop 0, the value of k is equal to 0. So there is going to be 2 root locus. Okay, n-2. Okay, so you tell me any comments. So what will you get, breaking point or breakaway point? Because the next step is to
Breakaway
find
point
the
at -2,
breakaway and
sir.
breakaway point. Yes,
Breakaway point at -2, sir.
breakaway point at, okay,
-2.
okay.
And
So
the
answer,
asymptotes are the root locus branches, sir, in imaginary plane,
okay.
complex plane.
So he's correct. So we'll get the breakaway point. Okay. So we'll be breaking away from the real axis to the complex plane. Okay. So we'll get the breakaway point. Okay. So how to get the breakaway point? Okay. So by using the characteristic equation. So you know what is characteristic equation, which is 1 plus k into gs hs. Okay. So let me, hs is equal to 1. So let me write this. Or what you studied in theory, this is numerator by denominator. Okay. This is equal to 0. Okay. So from here we will get the breakaway points. Okay, so let me call this as ds. Okay, let me call this 1 plus ks. Let me name this. Okay, let me write here, ds equal to this. Okay, so what we used to do, very simple, we used to differentiate this ds, okay, with respect to s. So what you'll get, 0 plus k. Okay, so you'll get this. So I'm going through the proper steps. Okay, it's very simple. So ds square, so what you, so this is differentiation of ns to ds. Okay, minus ns into differentiation of ds equal to 0. Okay, and how to get the points? So you put ns, numerator, we used to put numerator equal to 0. Okay, this. So if you put this equal to 0 and solve this, you'll get the breakaway or breaking point, and we'll confirm that point also. Okay, so let's first know what these values are. Okay, from the given plant transfer function. Okay, so ns in our case is equal to 1. Okay, and ds is equal to, okay, let me write the full transfer function. So we are given with this, k by s square plus 4s. Okay, so this is equivalent to ns by ds. Okay, k into ns by ds. Okay, so that's why I've written, I'm writing ns equal to 1 and ds equal to s square plus 4s. Okay, so let's, what you'll get if you differentiate it with respect to s, you'll get 0. Okay, if you differentiate ds, you'll get 2s plus 4. Okay, so just write this here, just put this into this equation, so you'll get 0 into ds. Okay, let me write full ds. Ds is s square plus 4s, okay, minus ns. So ns is equal to 1. Okay, so d dash s is equal to 2s plus 4. Okay, so this is equal to 0 minus 2s plus 4. Okay, so s, what you're getting, s you're getting is, okay, s you'll get is minus 4 by 2. Okay, which you'll get is minus 2. Okay, so we have to check. So this is on the real axis. Okay, s equal to minus 2. So we have to check for the value of k. If k happens to be positive, then we are sure this point s equal to minus 2 is breakaway point. Okay, so how to check that? Just put s equal to minus 1, okay, in this equation. 1 plus k into ns into ds. Okay, so let me do it. Okay, so, and what I am doing is check for k. Okay, or check if k is greater than 0 at s equal to minus 2. Okay, this is the process. Okay, so I'll be using k, this value 1 plus k into gs equal to 0. Okay, so 1 plus k, so gs you know is equal to 1 by s square plus 4s equal to 0. Okay, so k is minus s square plus 4s. Okay, so if you put s equal to minus 2 here, so what you'll get, 4 into minus 2. Okay, so this is 2 square is 4. Okay, minus 4 into 2 is 8. Okay, so this is minus 4, so you're getting k as 4. Okay, so k is positive, right? So k, we know k should be greater than 0, and we are getting k as 4, so this is positive. Okay, so, okay, s equal to minus 2 is break away point. Okay, we are just confirming it. If you see the root locus, you'll directly know. Okay, so let me just draw the root locus again. Okay, let me draw here. Okay, so we have 2 points here. Okay, this is 2 0 minus 4. Okay, and root locus is breaking at point. Okay, so that point is also the point of intersection for asymptote, right? Minus 2. So how the root locus will go? Okay, so use this color, green color. Okay, so root locus is going like this. Okay, because there are two root locus. Okay, k equal to 0 here, k equal to 0. As you increase the value of k, both the root locus, so this is root locus 1. Okay, let me change the color. So this is root locus 1 and this is root locus 2. Okay, and if you increase the value of k, they will move towards minus 2. Okay, and minus 2 is the breakaway point, so they will break away like this. Okay, so like this. So this is the root locus. Okay, so if you see at k, at infinity, you will have k tending to infinity here. Okay, so if you see, these are the asymptotes, right? making angle of 90 degree. This is 1 and we write this as minus 90. Okay, this point is 2. Okay, so this is the root locus. Okay, so I'm not doing the further steps where next step is like find the angle of departure and angle of arrival. So in this case we don't need that, right? So we don't have any complex pole of 0, so that's why we are not getting the values of those. And the next step was to find the crossover points. So if you try to find the crossover point, you will get s equal to 0, because the root locus is starting from the 0. Okay, so this is the root locus. Okay, so any doubt up to now? Any doubt you have? Okay, so the green what I'm showing here is root locus. Okay, so the root locus will break away from the real axis to the complex plane at point -2. Okay, so one root locus will be going to the positive j towards the positive j omega axis, or in the positive half plane, and the other will be in the negative half plane. Okay, so any doubt in this case? Okay, so what was the original question? So we have to find the stability, right? See, the closed loop system is stable for what value of k? Okay, so by looking at the root locus, okay, if you see the root locus, so what can we say? So what the root locus depicts is the closed loop poles, right? So you can see if k is greater than 0, okay, so closed loop poles are always lying in the left half plane, you can see. Okay, so what we wanted was this. Okay, so root locus should lie here, or the poles, closed loop pole should lie in this area. Okay, and the question was for what value of k it should be that the closed loop should lie in this side. Okay, so you can see from the root locus also, if k is greater than 0, root locus is always lying in the left half plane. Okay, so we just confirm the stability by drawing the root locus. So any doubt? Okay, I hope it's very clear.
Sir,
Yes.
sir, one pole is on origin. Sir, it will not. Sir, its effect should be here on stability, sir.
You can see, but k is not, if you put k equal to 0, then it's in origin. If you put k greater than 0, then it will be not on the origin. Okay, so if I put this equal to, not if I put this k equal to 0, so you can say it's not stable because it's marginally stable. Okay, if you
Yes,
get the step input, then it will oscillate.
yes,
But I'm putting k greater than 0. Okay, if you put k greater than 0, your root locus will be always lying in the left half plane.
yes. Okay, sir.
Okay, let system is state. Okay, we'll go to the next question. I think it is related to the same question. Okay, it is desired that the closed loop system obtained in problem 1 be an underdamped second order system. That would be true for all. Okay, so we'll be using this root locus. Okay, let me copy this root locus and please answer this. Okay, okay, so now you have to use the root locus. So what we want is underdamped system. Okay, underdamped second order system. So what is the characteristic for underdamped second order system? So if you see the roots, okay, so you had two roots, right? And
Complex conjugates, sir. They must be complex
yes,
conjugates.
okay, okay, what you're saying?
Complex conjugates, sir. They should
Yeah,
be not.
okay, so s1 and s2, so if you write, you'll get this complex conjugate terms, right? So I'm just writing exact terms. So it will be like this. Okay, minus omega n 1 minus it is. So these are two roots. Okay, so these are complex roots. Okay, so if you see this root locus, okay, let me just draw this. Yeah, now you see, okay, when are the roots, when are these poles complex? Okay, can you say? Okay, so when the root locus is leaving the real axis, what we can say is roots are complex. So I will just use the test points. So two test points I will choose. Okay, let me choose this point. Okay, okay, let me choose this points. Okay, so one point is here. So I hope this is visible. 1 second. Let me choose some darker color. Okay, so here I'll choose one value. Okay, this is S1 and this is S2. So what can you say? Roots are real, complex. What can you say?
Real, sir. Roots are
So
real.
roots, correct. So roots are real. So what can we say? The system will be overdamped, right? That we have
Yes, sir.
studied. Okay. So let me choose other points. Okay. Now if I choose here, okay, S1 and S2. If I choose here, what I see is S1 and S2 are conjugate pair, right? So they also have the imaginary part also. Okay, so imaginary part, what I have written here, this part is also there. Okay, and what is the characteristic for underdamped system? They will have imaginary part also. Okay, so if I have poles like this that I have shown S1 and S2, then the system is underdamped, right? So in this question we have to choose the value of k for which the system becomes underdamped. Okay, so what can you say? So in the previous question we have calculated the value at s equal to -2 is equal to k equal to 4. Okay, so let me write the value also. Okay, so here the value, okay, this question, let me rub this information is not required. Okay, so this point is -2. Okay, and what we calculated k is 4. Okay, so now you answer me what should be the value of k so that we get complex poles. Just look at the root locus and answer.
K greater than 4.
Okay, so what you can see is from k equal to 0 to 4. Okay, from, let me just define the regions. Okay, let me shade this. Okay, this, if you have root locus lying here, okay, the system is overdamped, and at -2 it is critically damped because roots are same. Okay, if I have k greater than 4, okay, if I have k greater than 4, what I will get is this. Okay, so roots will be lying like this. Okay, so that is the case of underdamped system. Okay, i hope I have made clear. If k is greater than 4, then the closed loop poles will be lying like this. Okay, any confusion? You just see from k equal to 0 to k equal to 4. Okay, so let me this also. So how the root locus is, so this is the root locus. root locus is like this. Okay, two root locus is like this. Okay, so what can I say? If you see, the poles are always real, right? So we have also seen, so this is the case of over damped system. Okay, I'll say closed loop poles are negative and real. Okay, okay. Now at k equal to 4, what is happening? Critically damped. Okay, or here I will write S1 and S2 will have only real part. Okay, that is negative or negative real part. Okay, okay. So in this case, critically damped means S1 will be equal to S2. Okay, negative real part still. Okay, and for k greater than 4, okay, so I'm drawing for k greater than 4. So this is k greater than 4. Okay, so you can see roots are lying in the complex plane. Okay, so the roots also have the imaginary part also. Okay, so what I will say is this is underdamped case. Okay, so S1 and S2 have both real and imaginary part, or S1 and S2 are complex pole. Okay, okay, so this answer is k should be greater than 4. Okay, so I have drawn the root locus also, and you can check from here also the cases, three cases, k0 to k4 over damped system, k equal to 4 critically damped system, k equal to k greater than 4, you will be having under damped system where S1 and S2 are complex poles. Okay, so this we have studied. Go back to your previous notes and just check this. Okay, so what are the poles for second order system for under damped case? So you'll have this. So any doubt? Okay, I will go to the next question then. Okay, so what is true about the underdamped second order closed loop system identified in the problem 2? Okay, so let's check. So in this question, it's all the options are asking about the settling time. Okay, so you have to find the settling time. Okay, from this looking at the root locus, we copy this. Okay, okay, so settling time. So you know what is settling time for the second order system? Okay, so this is the settling time. Okay, so how to find the settling time? So for settling time, you have to find the this eta into omega n. Okay, and also you know if you see roots of the second order system, so okay, so I'm using the same information, this information. Okay, let me write here once again. So S is minus eta omega n plus minus j omega n into 1 minus zeta square. Okay, this is how the roots are. Okay, and this is the real part, right? This is the real part of closed loop poles. Okay, so this is what closed loop poles of second order system under dam system. Okay, so we have to find eta into omega n, which happens to be the real part. Okay, so and what we have seen is if real part, so first how, when the real part is minus 2. Okay, so what is happening, you see this part again, we are concerning with this part. Okay, so always the real part of the under dam system is minus 2. Okay, so you choose any value here. Let's take the two values in at any k. Okay, so I'll choose this value, this value. This is s1, let me choose s2. Okay, so s1 and s2, so what we can see, its real part is always minus 2, correct? For s2 also, plus j, some imaginary value will be there based on omega n1 minus zeta square. Okay, so its real part is always minus 2, which is also equal to, so I want you to relate this and this and this, because ultimately what you have to find, settling time. Okay, and the real part of the closed loop pole is minus zeta into omega n. Okay, and from the root locus what we can see, okay, from the root locus, okay, let me write it down. From the root locus, this value is equal to 2, right? You see, this is the general closed loop poles of second order under dam system. Okay, and here this will be the equation. If you want to find any two under dam poles, okay, so poles will be lying in the highlighted portion. Okay, so I have chosen random s1 and s2, so you choose any points, real part will be minus 2. Okay, and I'm equating that minus 2 to this value, minus zeta into omega n. Okay, so what I'm getting, zeta into omega n as 2, and I will use that to get the value of settling time, which is, I put this, so I'm getting 2 seconds. Okay, very simple. I think this already it's covered in the lectures also, I think. Okay, so let's see the statements. It would have a settling time less than 1 second. No, it will not have a settling time less than 1 second. Okay, so this is wrong. It would have a settling time less than 0.5. This is also wrong. Okay, it would have a settling time less than 4 seconds. Okay, this can be true because 2 second is less than 4 second. Okay, because we don't have any option. Okay, so other is also wrong. It would have less than 1.5 seconds. So the third option, which says it would have a settling time less than 4 seconds, is true. Okay, so it will have a settling time of 2 seconds. Okay, so any doubt in this question? Very simple. Okay, we'll go to the next question. So it is desired that the underdam second order closed loop system identified in problem 2 have a maximum peak overshoot less than 10%. This is true only when. Okay, so this is, so let's, what is peak overshoot for second order system? It is minus eta into pi by root of 1 minus eta square. I hope this is into 100%. Okay, so this is the formula, and what you want is less than 10%. Okay, so this is our requirement. So let's first find the value of zeta. Okay, so what if I find the value of zeta, what can I get? Tell me. Okay, let me first find the value of zeta, then we'll see what we can do with the root locus. Okay, so let me solve this. Okay, and I will write this. We write less than equal to, okay, 10% is what? 1. Okay, we'll take the log on both sides. We'll get this. So natural log of 0.1. So what is that? So write in the chat box what is natural log of this 0.1.
Minus 2.302, sir.
Okay, minus 2.30, correct. Okay, correct. So I'll take minus 2.3. Okay, so let me square this. You'll get this.
Sir, it becomes greater than, sir, when you cancel minuses.
How much you're getting finally?
Sir, if you cancel minuses, we will get greater than, sir.
Oh, which one?
You cancelled minus, no, sir.
Okay, this one.
Minus zeta pi by root of 1 minus zeta square is less than or equal to 2 minus
Oh,
2.3
okay. You're saying
if you
that. Okay,
cancel.
this operation. Okay. Okay, I'm not certain about this. Okay, let me first find this and we'll see what we are getting. Okay. Okay, this is this. Okay. So you'll get this. Okay, 2.3 square by, this is pi square plus 2.3. So if you take the root, you'll get 2.3 by root of this pi square plus 2.3 square. So what is this value? I think 0.59 will get. Sure, 0.59. Okay. Everyone is getting the same. Okay, let me check this minus sign. Okay, otherwise if you change the sign, you'll get this. Okay, and zeta can be more than that. Okay, so let me just use this. It's okay. Let me use this root locus and we'll see how we can relate the zeta value to the angle. Okay. Okay. So okay. So how we can relate to this? So did you study this? Okay. So let's suppose. Okay. So S1 and S2. Okay. So for particular value of S1 and S2, you're getting zeta to be this 0.59. Okay. So what does it mean is it will make some angle, right? Like this. Okay. If I just use this. Let me rub this. Okay. This. And this is theta. And how we used to relate this theta? Cos theta is equal to zeta, right? So how do we get this zeta? Okay. So this is for this. Let's take S1. Okay. So this is, let's suppose this is one of the pole, closed loop poles. Okay, which is satisfying zeta. Okay. So it has minus zeta omega n plus omega n root of 1 minus zeta square. So this is real part and this is imaginary part. Okay. So what does it mean is this is real part, right? Which is minus 2. Okay. And this is the imaginary part. Okay. That we have to calculate. Okay. And how I got this angle, how to get this angle cos theta? If you use S1, so this I am not used J. Okay. So cos of theta is equal to real part. What is real part? This is, and what is the this part, hypotenuse part? It is summation of real part and imaginary part, which is equal to omega n. Okay. So this is omega n. So I'm just basically, this is direct formula, cos theta equal to zeta. Okay. So that's how we get the value of theta also. So how to get theta? You'll get cos inverse of this. Okay. Because if we get theta, we can get the imaginary part also. Okay. Let me first calculate the value of theta. So which is equal to cos inverse of 0.59. Calculate this in terms of a degree. You're getting 53.84. Approx this. What you're getting? Correct. Okay. So let's take this. Theta as 53.84 degree. Okay. So let me write here 53.84. So this. So this is, I was saying, this is omega n. Okay. So here this theta is equal to 53.84 degree. Okay. So this is there. So what I want to find is S1. What is the value of S1 in for our root locus? Okay. So we know the real part, we know the angle, and we have to find the imaginary part. So let me use the tan theta formula. Okay. So what is tan theta? Tan theta will be imaginary part. So this is magnitude I am taking. Okay. It's like magnitude, not the sign. Okay. So the imaginary part will be equal to, so I'm just assuming that we are taking magnitude, equal to tan theta into real part. Okay, so tan theta, tan of 53.84 into real part is 2. I'm taking the magnitude. Okay, so what is this value? You're getting 2.73. Okay, you're getting 134.6. Okay, then what is that? 134.6. Okay, I'm getting 2.73, or let me take 2.74 as the imaginary part. Okay, okay, I'm taking 2.74. Okay, so what I know is this S1, so I'm just substituting here with the calculated value. So now this is 2.j 2.74. Okay, this is minus 2 plus j. So this is the value. Okay, so what we can understand here. Okay, I'll just plot two region. Okay, so one region is this region. Okay, one region is this, and other region is this red one. Okay, let me choose different color, yellow one. Okay, so what do you think if I increase the magnitude of imaginary part, so what will happen? Okay, so let me write the imaginary part. What is imaginary part? You know, which is equal to omega n into 1 minus eta square, and we know this is underdamped system and eta is less than 1 or 0 to 1. So this is the value, right? Natural frequency is fixed. Okay, so imaginary part, what will happen? So what you should do to zeta, what your zeta value should increase or decrease in order for magnitude imaginary magnitude of imaginary part to increase or decrease? What do you think? So if I increase the value of zeta, what you will get? Imaginary part will increase or decrease. You see from here, if I increase this, what will happen to imaginary part? Okay, you just take some real values and check. So you check two values, you choose 0.1, you take other value as 0.5. So what you'll see, if I choose 0.1, okay, let me take omega n as some value. Okay, let me choose as 3 omega, let me say omega n is 3. So it will be 1 minus 0.1 square, 0.01. Other is what? 3 into 1 minus 0.5, 0.25. Which one is greater out of these two?
First, the second one.
Second one. How second one is greater?
So, so
Yes. Okay. Just, can you relate to this root locus? Okay. Because you see from here at this point -2, critically stable point -2, we are going into underdamped system. Okay. So underdamped system, real part is always fixed, that is -2. We are just increasing the value of imaginary part, omega into 1 minus zeta square. Okay. So what is happening? If I increase the value of zeta, okay, if I am increasing the value of zeta past this purple or magneta, what this color is, okay, purple, let's say, and if it goes into yellow region, okay, what I am saying is I am increasing the peak overshoot, right? Okay, so zeta is related to peak overshoot, right? Okay, you choose first, you get this two values. This is 3 into root of 1 minus 0.1. So this is 2.984 and this is 3 into root of 1 minus 0.25. So this is 2.59. Okay, so these are two values, right? So what we can say, which one is greater? This one is greater, right? Okay,
yes, sir.
this one is greater. So let me plot in the root locus. Okay, so how to plot in the root locus? Let me change the same. Okay, so we have two poles here. Okay, and we are concerned with this. Okay, so I have chosen two values, two zeta values. Okay, so one zeta correspond to this. Okay, and other zeta corresponds to this. Okay, so and you can see in the first part when zeta is equal to 0.1. Okay, so I can say this corresponds to zeta equal to 0.1, right? And the other one corresponds to zeta equal to 0.5. Okay, for our case here, if you see, okay, if I, so we are talking about these two cases, right? So I am doing this discussion because of these two cases. Okay, because what should be the sign, right? So if zeta is less than 0.59, okay, so if zeta is less than equal to 59, then it will follow which portion from our discussion? Can you tell me? You see, at zeta equal to 0.1, we have this green one, and at zeta equal to 0.5, we have this blue one. Okay, if I increase the zeta, you will get this one. If I increase further, you will get this, and if I increase the zeta, sorry, if I decrease the zeta, you will get this. So this is 0.1. You can say zeta is 0. What you can say below that is 0.9. Okay, and let's suppose here I choose value zeta equal to 0.6. So you see which sign should I choose? If I want the purple one, okay, so this is first. Which sign should I choose? First one or second one?
The first,
Huh?
the first one.
First one. Okay. So why we are choosing first one? Everyone is clear. Okay. Okay. So this we have to choose. Okay. If we choose zeta to be greater than 0.59, you'll be getting the region here in this. So I'll just relate this to this region. Okay, that's what we want. Okay. So our friend was correct. So if I do this, we have to do this, I think. You just see the mathematics of inequalities. Okay. I'm just checking with the root locus and I'm getting this correct answer. Okay, you just do the analysis for yourself. So you'll get this. Yes. Okay. If you have zeta greater than 0.59, you'll go into the yellow portion. Okay. That you have seen from the analysis. Okay. So up to now, what we got this. We got the imaginary part also. Okay. And what was the original question? So what should be the value of k at this point? Okay. So we know S1 and S2. Okay. So now we know S1 is equal to minus 2 plus J 2.74 and S2 as minus J 2.74. Okay. So now what we have to find out, what should be the value of K. Okay. So how to find the value of K? Again, same thing. So we have to use this V plus K into GS equal to 0, 1 plus K into GS equal to 0. Okay. So 1 plus K, what is GS? It is equal to S square plus 4S equal to 0. Okay, K is equal to minus S square plus 4S. And if you put S equal to minus 2, okay, minus, let's put this whole square, okay, use this bracket, plus 4 into minus 2 plus J 2.74. Okay, so what value you will get? You have to use the calculator in this case. Okay, so this minus 2 plus,
Sir,
so what you're getting?
sir, S plus 4 into S, right like that, sir.
I'm getting
Minus of S into.
11.50. Yes.
And we write S plus 4 into S, so like that we will get easy, sir.
once again you repeat. You are saying you have to write s equal to.
No sir, minus s minus of s square plus 4s is equal to
Mm-hmm.
s into s plus 4 sir. Then minus 2 plus 2.74 into
Acha, you are
2.
just okay. You are what you are doing is this. Okay, you're just using this. Okay, this a plus b whole square. You are saying.
No sir,
Then
s square plus 4s is there now sir in first step.
yeah, yeah.
K is equal to
Mm-hmm.
that we can take s common sir.
Yeah, you're saying okay. Okay, okay. This you're saying.
Yes sir, one is 2 point minus 2 plus 2.74
This minus 2 point j 2.74 and
into
minus 2
2
plus j 2.74 plus 4.
2 minus.
This you're saying? Okay.
Yes sir, then now calculate sir.
Yeah. So I've done the calculation. So okay. So this is simplified step. Okay. So our friend has simplified the step from here to here. So directly I have put the value. So I got this 11.50. Kindly check. I hope you will get the same answer. Okay. Approximately you'll get the same answer. This one. Okay. So let me check. Okay. So let me again redraw the root locus and explain what we have done. Time is also not there. Okay. So this is there 0. Okay. So our root locus was like this. So this is 2. So okay. So this is the root locus and we have identified this point. Okay. Okay. So these 2 points. Okay. So if this k is equal to 4 and this now we have identified k is equal to 11.50. Okay, these 2 points, and again if it will go to infinity at k equal to infinity. This we know because it start from here. Okay, so what we know now is if k is between 4 to 11.50. Okay, this point is also k equal to 11.50. Okay, so this is okay. Let me keep it this way. So if we have this portion, if we have root locus in this region from 4 to 11.50, we'll have maximum overshoot, okay, less than 10%. Okay, this we have just now calculated. So what I did was I just assumed this point to be S1 and S2. Okay, that's how I have done the calculation. You go follow the steps. Okay, S1 and S2. Okay, so I got the value of 11.50. So correspondingly for S2, which is just you keep minus j, minus j minus 2 into 2 minus 2 minus j 2.74, you will get same answer 11.50. Okay, so if you see the option, okay, you'll get the first. So okay, should be this. Okay, quickly we'll go to the next question. This time is not there. Okay, which one of the following statement is true about the locus of closed loop poles of problem 1? Okay, so the root locus always lies in the left half complex plane of s equal to 0. So again what I will do, I'll just take the root locus and dash is okay. This is the root locus. Let me take this and we'll comment on all the options. Okay. So which one of the following statement is true about the locus of closed loop poles of the problem one? You see, first statement says the root locus always lies in left half complex plane for k greater than 0. This is true, I think, yeah. You see, it always lies in left half complex plane. Okay, you can see here that already we verified in the question number 1. Second statement is the root locus lies in both the left and right half complex plane for k greater than 0. This is wrong. Okay. Third option is the root locus lies always on the real axis for k greater than 0. This is also wrong. Okay, because at s equal to -2, it emerges from real axis to complex plane. Okay, this is also wrong. The fourth statement is the root locus lies always on the imaginary axis for. This is also wrong. Okay, I hope there is no doubt in this. Directly by seeing the root locus, you can answer this. Okay, again this problem, a second order system is governed by this. The number of state variable required for representing the state space representation is. So if you see this equation, it's a second order equation, right? So what we have studied, so we studied that this is second order state, second order ODE, which can be represented in, which can be represented as two first order ODEs by taking two state variables. Okay, so this is, you can see this is second order equation. So let me write the state equation. Okay, this is second order equation. So what we take, we'll take two state variables. Okay, two state variables, then we will write into two first order ODEs. Okay, that we call state equation. So let me do it. Okay, so let me choose this state variable first. Let me choose x1 as y. Okay, so if I do x1 dot, we got y1. Okay, let me choose x2 as y dash. Okay, so if I do x2 dash, okay, so this is x2. Okay, and what is x2? Okay, so you can get x2 by using this equation. Okay, so let me rewrite in terms of x1 and x2. So which is equal to y double dot. Okay, so you have to write y double dot here. So let me write into the original equation in terms of x2 and x1. Okay, so this is, okay, let me write original equation first. Y double dash plus 5 plus 6y equal to 8. Okay, so you know this is x2 plus 5 x2 plus 6 x1 equal to u. Okay, so what is x2 dot, which is u minus 5 or 6x1 minus 5x2. Okay, so you can write here u minus 6x1 minus 5x2. So this is equation 1, this is equation 2. So these are two state equation that you can write in matrix form. Okay, you know matrix form general is this ax plus bu. Okay, so I'll write these two equation in this form. So this is x1 dot x2 dot, okay, so let me just take the space and simplify. Okay, so I'll write here. So what are two state equation? I will just copy here. So first is x1 dot is equal to x2, because we have to write in terms of x1 and x2. And again second equation I got is u minus, let me write first, 6x1 minus 5x2 plus u. Okay, these are equation 1 and equation 2. So I'm writing in matrix, okay, in this form. Okay, so this will be x1 and x2, and this will be output. Okay, so let me just fill this. So what is the coefficient of x1? This is equal to 0, this is 1, and this is minus 6, this is minus 5. Okay, and if you see, output is equal to 0 for x1, and second case it is equal to 1. Just check. Okay, so I'm writing equation 1 and 2 in this matrix form. Okay, we'll get the same equation, x1 dot equal to x2. Okay, which is, so if you see how to have written, x1 dot is equal to 0 into x1 plus 1 into x2 plus 0 into u, and x2 is equal to, x2 dot is equal to minus 6x1 minus 5x2 plus 1 into u. Okay, so I'm writing in, you can see this equation x1 and x2 and this equation are same. Okay, just I have written in the matrix. Okay, so this is state equations. Okay, so let me write the output equation also. So this is the general form for state equation. Okay, just highlight this. And what is output equation? You know, y equal to cx plus du. Okay, this is again the general form, and we'll try to write for this type of equation also. Okay, so just see this output. Okay, so this is, I'll use this equation, so I'll just highlight this, y equal to x1, because that is the output we are choosing. Okay, y equal to x1. So if you write in terms of matrix, what you'll get, you'll get this 1 0 x1 x2 plus, what is d? D is 0. Okay, if you choose this is 0 0, right? So you can write like same as writing 1 into x1, okay, plus 0 into x2, but this is wrong, this is 2 into 1, and this is 1 into 1. Okay, so I should not get 2 into 2. Okay, anyway, you write this as 0. Okay, 0 into u. Okay, which is same as writing y equal to x1. Okay, so what you can see, this is a, this is b, okay, and this is c, and this is d. Okay, a b c d, which characterizes the plant. Okay, for which the equation is given already. Okay, so let's answer the questions here. So this was very simple. The number of state variable required for representing this state space representation is already, we know it's 2, okay, because of the order. Okay, let us answer the other questions. The state matrix for the system in problem 6. Okay, so already we have calculated this. So this is the state matrix: 0 1 minus 6 minus 5, 0 1 minus 6 minus 5. This one, second option. Any doubt in this case? You see, so I have chosen x1 equal to y, so very important. And what is x2? X2 is y dot. Okay, correspondingly I got x1 dot and x2 dot in terms of x1 and x2. Okay, so that I can write the equations in this form. Okay, so let me just copy that matrix, and so the answer is here, this. So this is A matrix, state space. Okay, state matrix is given by this. So it is the eigenvalue of the state matrix obtained in problem 7. So how to get the eigenvalues? So lambda I minus A, you get the determinant and you just put it equal to 0. Okay, so this is the identity matrix multiplied by lambda. So it's like this, and you're just multiplying lambda. So I'll just return lambda here, minus A, which is 0 1 minus 6 minus 5. I think 0 1 is 6 minus 5 equal to 0. Okay, not equal into, first we are finding the matrix, then we'll take the determinant. Okay, which is equal to lambda, this is minus 1 6 lambda plus 5. So this is the matrix, and now we have to take the determinant. So this is lambda I minus A, and let's take the determinant of that. So it will get lambda into lambda plus 5 minus 1 into 6, which is lambda square plus 5 lambda, which is plus 6. Okay, and if you find the roots of this equation, so the roots of this equation are the eigenvalues for state matrix. Okay, so what are the roots? So you can write in this form. Okay, so one of the root is 2 and other is 3. Okay, so eigenvalues, one eigenvalue is equal to minus 2 and other eigenvalue is equal to minus 3. Okay, and also you'll see, if you find the transfer function, minus 2 and minus 3 will also be the poles of the particular transfer function. Okay, for this eigenvalues of the state matrix obtained in 7 is minus 2 and minus 3. So any doubt in this? We're just finding the eigenvalues by doing this lambda I minus A and determinant of lambda I minus A equal to 0. Okay, that's what I have done, and find the values of lambda 1 and lambda 2. Okay, go to the next question. The input vector of the state space realization of problem 6 corresponding to state matrix. So it's asking input vector. Okay, what is input vector? You see B matrix. Okay, 0 1. So they're asking B 0 1. Okay, so the first option is correct. Okay, very simple. So already we have found out the ABCD. The output vector of the state space realization of the problem 6. So output vector is C. So what is C? Let's check. This is C 1 0. Okay, so you know this is 1 into 2 and this is 2 into 2 into 1. Okay, so you'll get 1 into 1. Correct. 1 0. So output matrix is this. C. Okay, so they're asking the transpose of this. It will be 1 0. This one. Okay, so any doubt? Simple. Okay, using the relationship between the transfer function and the state space realization, the transfer function of this system can be calculated. So you have to find the transfer function. So let me see again other questions. Very simple. Okay, so this is very simple question actually. Okay, so you have to find the transfer function. Okay, so we'll start from here. x dot is ax plus pu. Okay, and other equation you know is equal to y equal to cx plus tu. Okay, so what we used to do, we used to take the Laplace of x dot. So what used to get s into xs minus if xs. Okay, let me write x. Okay, equal to bu. Okay, and x is what, si minus a equal to bu, and x is equal to si minus a inverse of p into u, and you put this here into y, what you will get, c into si minus a inverse, okay, into b into u plus t into u. Okay, if you find y by u, which is c into si minus a inverse p plus t. Okay, that's how you'll get the transfer function. Okay, so we'll use this to get the transfer function. So what is important is first we'll calculate the si minus a inverse of that. Okay, so that's very important for us. Let's first calculate si minus a. So si minus a is, this is 2 into 2 matrix. Okay, so a is, we know, 0 1 minus 6 minus 5. So what you'll get, s minus 1, this is 6, s plus 5. Okay, we'll find the adjoint of that. So directly I'm writing. Okay, so it's a matrix thing. Okay, so it is, you can, if you want to find si minus a of inverse, what you do, you take the adjoint of this si minus a. Okay, and take the determinant like this. Okay, so first I will find the adjoint. So directly I am writing it. Okay, please confirm. So you'll get s plus 5, this is minus 6, get 1. Okay, directly we'll get s. Okay, so if you do find out, what you'll get is s plus 5 1 minus 6 and s. Okay, so this is the adjoint, this is not the adjoint. Okay, so finally I'll get this as adjoint of this. I hope this is correct. Okay, what is si minus a determinant? So here you can find si minus a, which is s into s plus 5. Okay, from here I am finding out s plus 5 minus of minus 1 into 6. So this is s square plus 5s plus 6. So you'll get 1 by s square plus 5s, sorry, just writing here, square plus 5s plus 6. And what is the inverse? Si minus a inverse is, you know, adjoint of si minus a by the determinant of this. So which is s square plus 5s plus 6, and this is s square plus 5 1 minus 6, and this is s. Okay, let me check once more if I'm getting anything. Okay, okay, I hope this is correct. Okay, so let me put this si minus a in original equation. So what is y by a, y by u? Okay, again let me copy this equation. Okay, so what is c? So c is, so what was c? 1 0. Okay, so this is 1 0. Si, just now we have calculated this to be 1 by s square plus 5s plus 6. Okay, I'm just keeping it out of matrix. You can multiply also. So what is B? I think B was 1 0. Let me again check. What is B? B was 0 1. Okay. Okay. B was 0 1. Okay, let me correct it. Because otherwise, so this is the processor. Okay. D is equal to 0. So let me just see what is the matrix. So this is 2 into 2 matrix. This is 2 into 1 matrix. Okay. And this is 1 into 2 matrix. Okay, because ultimately if you multiply all of this, you have to get 1 into 1. Okay, so let me first do the multiplication of these two matrix. Okay, so what you should get is 2 into 1 matrix. Okay, so let me take this s square plus 5s plus 6 outside. Okay, so what you'll get is s plus 5, you'll get 2 into 1. Okay, so s plus 5 into 0 and 1 into 1. Okay, let's see, I'm getting any mistake. Okay, this is s plus 5 into 0 plus 1 into 1 minus 6 into 0 plus s. Okay, now this is 2 into 1 matrix and we are multiplying with 1 into 2. This is 2 into 1, this is 1 into 2. Okay, we'll get 1 into 1 matrix. Okay, finally square plus 5s plus 6. Okay, just multiply this. So if I just, okay, let me do one more step here. So this will be 1 0 and this will be, you'll see 1 ns. Okay, again you what you'll, if you multiply these two matrix, so again let me write, this is 2 into 1 and 1 into 2. Okay, so what you'll get is square plus 5s plus 6. So 1 into 1 is 1 into 1 is 1 plus 0 into s. Okay, so what you'll get is out of this 1. Okay, so again, so this is the matrix s square plus 5s plus 6 into 1. Okay, so I'm not writing 1. So this is y by s u of s. So this is the transfer function. Okay, s square plus 5s plus 6. S square plus 5s plus 6. So this one. I hope this is very clear. Okay, just follow the steps. So I'm getting the, so let me just quickly finish the questions. So consider a stable ATI system that is provided with a sinusoidal input having a frequency of 12 hertz. Okay, so input is sinusoidal with 12 hertz frequency, then the corresponding steady state output would be sinusoid having a frequency of, so we know it has same frequency. Okay, you just remember this expression. What was that? Okay, u naught, okay, p j omega sine omega t plus phi. Okay, so you just see, and we know, okay, so u of s, what was the frequency? If u of s is, let's suppose this is u. Okay, so what is the frequency of input, this omega naught or 2 pi f? Okay, so let me again write omega as 2 pi f. Okay, so 2 pi is again constant. Okay, so just observe these two. This is the output and this is the input. Okay, so the frequency is same, that already we have seen. So that's why the corresponding steady state output would be sinusoid having a frequency of 12 hertz. Okay, I think that there will be no confusion. Input and output frequencies are same. And the transfer function of a plant is this: the magnitude of sinusoidal transfer function at an angular frequency of 1 radian per second. Okay, very simple. So let me say this is PS equal to S plus 2, S plus 4, and we have to find the magnitude. Okay, so what we used to do, just put j omega here. Okay, so j omega plus 2, this used to be j omega plus 4, and if you calculate the magnitude of this, what you will get is 2 square plus omega square, and this will be 4 square plus omega square. Okay, and we have to find at omega equal to how much. So this should be at 1 radian per second. Oh, let's find out. So what you do, just put 2 square plus 1 square, omega equal to 1 you have to put, and this will be 4 square plus 1. This will be 4 plus 1. This will be 4 16 plus 1. Okay, I will write 16 plus 1. Okay, it should be 4 by, sorry, 5 by 70. Okay, 5 by 70. So what is 5 by 70? 0.29. Getting 5 by 17. Okay, we have to take the root also. Okay, 0.53 I am getting. Okay, write this as to be 0.54. Okay, very simple. Okay, so this is how we calculate the magnitude. Okay, in the next question we have to find out the phase. So how to calculate the phase of this. Okay, I'll just copy this. Okay, the process is same up to here. Okay, so we have to find the phase of this. So what is that? Tan inverse of omega by 2 minus tan inverse of omega by 4. Okay, this we have to find out, and simply you can use the identity also, which will be equal to omega by 2 minus omega by 4, 1 minus omega by 2, 1 plus omega by 2 into omega by 4. This also you can do, and individually also you can put the value. Okay, and we have to find that omega equal to 1 radian per second. Okay, so what is that? Let me put 1 by 2 minus 1 by 4. This is 1 plus 1 by 2 into 1 by 4. So it will be equal to tan inverse of 1 by 2 is 0.5 minus 1 by 4 is 0.25. Okay, this is 1 plus 0.5 into 0.25. Okay, just quickly what you'll get, just find out. So we'll be taking tan inverse of 2 by 9. 12.52 I'm getting. So let me write as 12.528 I'm getting. Okay, so 12.53 degree. So this is at omega equal to 1 radian per second. This is 1 second. Very simple. Okay, just plug in the values. This is how we calculate the angles. Okay, I hope I am doing the right calculation. Okay, but the process is same. So let me just quickly do this last problem. In problem 13, the ratio of magnitude of sinusoidal transfer function at an angular frequency of 10 is to that. Okay, so we have to find out what magnitude. This is at omega equal to 10 radian per second. You have to find the ratio of this. This was at 1 radian per second. So already we have calculated the denominator. Okay, so you have to calculate this. So what was that? This was 2 omega square plus, sorry, 2 square plus omega square. This was 4 square plus omega square, and by already we have calculated it. Okay, this was 0.54. Okay, so I'm not calculating it. This is 54, and also I'm just saying here omega is 10 radian per second. Okay, just general formula read I have written, that's why I'm writing like this. So what you do, just substitute 10 square, 2 square plus 10 square, 4 square plus 10 square by 0.54. Okay, which is what, if you see this value, which 10 square is 100, right? 100 plus 4 is 104, and this will be 116 by 0.54. Okay, so 4 by 0.54. Okay, this is what I'm just writing, 0.94 by 0.54. I'll get. Okay, 1.74 I'm getting. Okay, 1.74 I'm getting exact. Something. Okay, so this is the ratio. I hope this is correct. If everything is correct, I'll get the same otherwise. But the process is same, right? You're getting how to find the magnitude, right? So this is how we calculate the magnitude, and just ratio is fine. Okay.
Sir,
Yes.
sir, model paper is MCQ, sir.
Okay. MCQ. So you have asked them.
What is the model paper, sir? All are MCQ and MSQ, sir. Fill in the blanks also, sir.
Okay. You're saying about the final control system exam.
Yes, sir. Final exam.
Final exam, that I don't know. I am not confirmed. Like, I think you're the one that in the previous tutorial you asked them. You have you mailed them? Like any response you got?
No, sir. I didn't got, sir.
Okay. Then I'll ask, because I think when you are joining the course, they will write like what will be the type of exam, end exam.
Yes, sir. They wrote MCQ, sir. But what about negative marking, sir? Is there a
Okay,
negative
okay.
marking?
Negative marking. Okay, your concern is about the negative marking. Okay,
And
okay.
can we carry calculator to the exam, sir?
That I don't know. I think for
Once no,
this
sir.
control, because you are using complex. I don't know. Like, I hope like they will allow the calculator, because this is not, because you have to use the calculator. But I have to confirm. Like, I have not checked the, like, what is the, like, at the end what is the procedure for conducting the exam.
No,
Okay,
calculator
sir.
they are not allowing. Eh?
Okay, calculator they're not allowing. Oh, okay, okay. I have to check. I have not seen any guideline. Like,
Then, if they don't allow calculator, there is on-screen calculator, sir.
I hope there will be.
Yes, Google calculator you can use.
Okay.
Google calculator, sir. Then gate calculator or
I don't know, because I have not seen the guideline. Like,
once no, sir.
okay, because I think on the internet you'll find this information, because in PTL, like, lot of exams they are conducting. Like, I
Some
think
are
the procedure.
saying a negative marking is present, but some are saying negative marking is not present, sir. We don't know
Okay, I think
what
that
is
is
the.
course dependent. So, okay, maybe I'll drop one email to the authorities, and if I get the response by the next tutorial, I will share it with you.
Okay, sir.
Okay, so any doubts in today's tutorial? Okay, so I think last questions were very simple. Okay, okay, but you understand, like, what is the significance of root locus by these examples? Okay, so I have not done any mistake. Okay. Just do these examples by yourself and just figure it out. if you're getting the same answers. Okay. Okay, because my solutions can be wrong also. Okay, you just verify with the lecture notes also. Okay, so I'm hoping that there is no doubt. Okay, so I'm already okay. I'm closing the session. Okay, so thank you for attending the session. So I'll meet in the next session. Okay, so do see the week 9 videos. Okay, thank you.